introduce Irina Rish. Irina Rish is a full professor in the Computer Science and Operations Research Department at the University of Montreal and a core faculty member of MILA Quebec A Institute, where she leads the Autonomous AA Lab. She holds a Canada Excellence Research Chair in Autonomous AA and a Canada Institute for Advanced Research, C for Canada AA Chair. Irina's current research interest includes training and analyzing the behavior of large-scale neural network models, or foundation models, neural scaling laws, as well as continual learning, out-of-distribution generalization, and robustness at scale, to name a few. So um, I would like to add to this bio that Irina is also one of the very few academic researchers who is really up to the industry level competition in designing open source language models, large language models. So she has been doing a lot of pioneering work in the field of foundation models and making them open source. So thank you, Irina, for accepting our invitation.
Yeah. Oh, thank you. Thanks for a nice introduction. Thanks for inviting me. Okay, let me just. Yeah. Okay, you can hear me well? Okay. So, as I understand, there was also an interesting talk yesterday on similar topics. Yeah, so I guess I mean, you can't ignore the elephant in the room, like whatever research you're doing, you can't ignore the advent of all these foundation models and scale in whatever way you can kind of take it into account. And as Saras mentioned, yeah, I mean, getting compute in order to do actual experiments might be non-trivial. I'll talk about that. It's possible, but not trivial. And doing a bit more of a kind of, indeed, academic studies about scaling laws is something that we can probably do in any case, even with limited compute. But ideally, you would like to do both. So this talk is kind of a bit of a just an overview of some recent developments, some work in progress. It's still incomplete. So I'll see how it goes. But it all starts basically with like, it's not just continual learning. I mean, I always kind of start thinking back, not just recent AI and deep learning, the whole machine learning and the whole statistics back like, I don't know, 50, 60 years ago, it was always driven by main question of generalization, right? So just statistics was much simpler and generalization was within distribution, and the models were perhaps like regression, linear or non-linear, but just models became more complex. The question remained, and the notion of generalization started becoming more and more general. And that's why people started talking about out-of-distribution generalization, transfer, meta-learning, and so on. It's all about like trying to going further and further from the data you trained on. Continual learning is just a particular setting, but it's kind of the same problem. Just like happens sequentially, it makes life more complicated because if you have all your kind of data available at once, it's easier to learn a joint model that can rule them all. If data are available sequentially, as we all know in continual learning, yeah, you have less information at each point, and it's harder to find solution that will be simultaneously good for different distributions. But the thing is that with all this recent advance at large-scale models, essentially what they're claiming, or at least, I mean, starting with the GPT-3 paper, that they are few shot learners, that they do generalize much better than anything you've seen before. And which kind of raises the question like, yeah, so you definitely need to see how that scaling relates to your specific field of kind of setting of generalization. So yeah, we all kind of know how it started, and back in 2020, with kind of release of GPT-3, and then there was this whole avalanche of these large-scale models, not necessarily language models, multimodal, and so on and so forth. Stanford, basically a large group of people at Stanford wrote that paper in August 2021, and now there is a Stanford Center for Foundation Models led by Percy Liang and others. And by the way, there is a company called Together that's associated with that research center and others, and we collaborate with them on like building actual large models. So the idea was that maybe if you pre-train an unsupervised way models on extremely large and diverse, and the key is diverse, without defining it kind of formally, set of data, that hopefully the models, if they're large enough to incorporate this information, they will kind of know about most of the typical ways that data distribution goes. So whatever comes their way later, they can probably recombine that knowledge, and just with few examples, they can take care of the tasks at hand. And not only that was observed kind of empirically, I mean, all of you probably have seen, and some probably too many times, those famous straight plots. Well, they're not necessarily always have to be straight. I'll talk about that later. But kind of more formally, people try to analyze like performance in different kind of metrics, but say this is for the kind of just a loss on the test or validation data. It's not performance on particular task, but it's kind of exemplary of what's going on. And Jared Kaplan and colleagues back in 2020, actually even end of 2019, had this paper which kind of builds on lots of previous years of research on how performance scales in neural nets, actually dating back to 1994. To the best of my knowledge, the first scaling paper for neural nets was by Karina Cortez and Vladimir Vapnik and others at NeurIPS, well, NIPS back those days, 1994, which actually showed, at least with data increasing on x-axis, that performance kind of follows. In that case, it was, I think, a classification task that follows power law. Anyway, so there was lots of buzz around this type of observations. There were many papers since, and then Jared's paper kind of somewhat, well, basically confirmed that and also introduced the scaling for compute. So the meaning of those things, those three plots that many of you might have seen even on various T-shirts people were wearing at Mila in the past couple of years. The meaning of those was that essentially, surprisingly, the performance of neural nets, at least in this case, just test loss, can be captured by three very crude variables. Essentially, the amount of compute available, like if you increase that compute, and at each point, like you're given certain compute and you try to find like the optimal amount of data and the model size, and you kind of choose that, so that best result, or at least approximation of that, follows power law. And same thing with dataset size and parameters. So the surprising thing to me and to many is that how crude those measures are, because effectively dataset size is an extremely rough approximation to what you really wanted to measure, the amount of information and the data. It's kind of assuming that in real life we'll be like crawling the whole web and the data are diverse enough, so there's lots of information, and that's why dataset size is reflecting that. But of course, worst case scenario, one can just repeat same sentence as many times and then you won't learn anything. So of course, it's not just the size that matters, obviously, but given like all reasonable assumptions about training, that data are diverse, size seems to be like one of these critical variables. And the number of parameters in the model, of course, what you really wanted to measure would be like the capacity of the model. And it's, again, surprising that just a simple variable such as just number of parameters seem to be kind of very predictive and important for telling how the performance will evolve at scale. Anyway, the interesting thing is, and I probably should start moving a bit faster, it's not just transformers and some other complicated architectures that seem to be showing the kind of scaling with increasing amount of, say, compute. The recent paper on scaling MLP says, well, I mean, of course, the scaling is probably much slower and less efficient, but even multi-layer perceptron at sufficient scale seems to be doing much, much better than at lower scales. And there are interesting discussions a couple of years ago that maybe you can just like, all you need is MLP. But of course, it's not a practical type of architecture to scale. So anyway, it all kind of goes back to this, yeah, my favorite quote from Rich Sutton. Everyone here has seen this bitter lesson, probably article many times, but the lesson was that in the whole history of AI, people first try complicated tricks, algorithms, models, and everything. And there is always question on the back of our mind, will that stand the test of time or not? So it may or may not, and you need to be careful about that because indeed, like all the complicated systems for playing chess, well, kind of later when compute became available, just kind of replaced by much more like straightforward systems, right? So the same now may apply to all the algorithms and models that we were developing, all the inductive biases. And the question is like, which one will stand test of time or what test of time and which will not. And in order to check that, you might kind of want to use those like scaling trends. So essentially you can view scaling as your investment tool. If you compare architectures, you compare, in this case, vision transformers versus convolutional networks, right? So yes, convolutional networks were state of art, and they kind of remain, I guess, state of art in various settings. But when the data became like really abundant, the situation may reverse. Vision transformers cannot perform them, and it's okay. I mean, there is no single like winner takes it all model or algorithm. You kind of want to know the full spectrum, and you want to know when to use what, and what to use at scale, what to use at medium scale, what to use at small scale. So that's why I think it's just the scaling plots are more of a kind of a proper way of reporting and evaluating the performance of different methods as compared to simple kind of single point tables for specific data sets, for specific model sizes and so on. So this gives you a fuller picture. So going now to continual learning, how the scale played out in the last couple of years, and what did people start observing at scale? Because I mean, as I said, I mean, if you increase the model size, pretraining data size, and claim that models become few short kind of learners and can generalize better, well, that hypothetically should help also in continual learning, where you can see all the new tasks and old tasks. Well, I mean, you can treat old task as a new task and say you should be able to adapt to that in a few short as well. And anyway, so there was this paper last year, kind of, I think one of the first papers on scaling and continual learning that actually in simple setting try to evaluate what happens with a standard stability plasticity trade-off. So if you, it was in case of well, vision transformers, ResNets, they were actually kind of pre-trained like on ImageNet, and the question was like, if after that you can still keep fine-tuning and do continual learning, but on top of the large model, what will happen with catastrophic forgetting versus adaptation, or stability versus plasticity? And what they observed, and again, I'm kind of repeating things many of you probably have seen multiple times, the papers last year I clear, but it was kind of interesting observation that even made some people make bold claims that scaling solved continual learning. Well, I would say it is significantly alleviated catastrophic forgetting, at least in the cases people studied. So what we see here from that paper is that if after the model is pre-trained, you start kind of doing continual learning classical setting. First, you train on or fine tune on task A, and then switch to task B, and you measure accuracy on both as you go. Then the larger the pre-trained model, and in this case, the dark color shows like the smaller models, and the lighter colors are bigger models for different architectures. For example, in the middle, you see like ResNets of different size. On the left, you see vision transformers. Bottom line is the larger that pre-trained model, the better is a subsequent stability plasticity trade-off that you will observe when trying to switch between different tasks. Again, let's keep in mind that these results are for specific empirical setting, and the tasks are visual, and the question, many questions, how all that would hold, or would it hold if the continual learning tasks would be drastically different from what the model was pre-trained on. So that's where all the current research on scaling and continual learning probably should go. This is like promising initial observation. It's far from saying that scaling solved continual learning. But it can be helpful for sure, and not just for two kind of problems. Again, from the same paper, they say, well, it seems to be also helping to improve that trade-off, even if you keep going and you have like 10 tasks in a row instead of 2 tasks. There is not much forgetting here. They kind of were showing like 10 tasks from the split C400. Again, the critique could be that, of course, you pre-trained like on ImageNet. Now you are doing continual learning on C400. Just how different are those distributions? Like you kind of pretty much learned something that's very, very close to your so-called new tasks. How new are they? Good point, exactly. So that's where I think, again, research should go, and we should measure diversity between the previous and subsequent tasks, between pre-training data and the kind of downstream data sets, and basically keep asking the same questions and see how they will be answered in a variety of situations. And we need to have like control variables that we can push, see what happens. But again, so this was just a promising indication of what can happen with large pre-trained models, and how increasing them seems to be improving your trade-off between forgetting and adaptation, and so on and so forth. They also showed kind of initial promising results for language, not just for images. Again, in particular metrics, so they basically were just evaluating accuracy of predicting the next token on particular data sets. Again, so it's all promising, but by no means I would say that this type of results can make you jump to conclusion that scaling solved continual learning. Anyway, by the way, a little bit of a detour, and well, I guess shameless self-promotion, or shameless student work promotion, but it's kind of relevant because scaling laws, whether it's continual learning or other things, are not necessarily always straight lines on log-log plots. And that's kind of also part of the research in the group. We were trying to figure out like what to do about that and what would be a better fit. So that recent work on broken power laws, or broken neural scaling laws, in this case takes results from that paper, the clear paper I was showing, and actually finds much better fit, because if you look carefully at all the scaling plots, well, majority of scaling plots in that paper, as well as in many like chinchilla paper, people fit straight lines to clouds of data which clearly look like pieces of some nonlinear function. So we kind of wanted to investigate that, take care of that. There was this paper last day clear from the group on family of kind of more general family called broken power laws or broken neural scaling laws, which are essentially a combination of potentially large, but in practice usually no more than 2, 3 pieces, where each piece is power law. So essentially it's just extending the old wisdom to more complicated cases, and shows like how to fit it and what can it kind of model well. I'm not going to go in the details because I think it's all in the paper, and we are almost at the half of the talk. But the idea is that the parameters of this functional form, they control kind of how sharp are the breaks between power law segments, and how many of those breaks are there, so on and so forth. And it seems to be so far the simplest in terms of smallest number of parameters functional form that at the same time could capture really, really wide variety of scaling plots in wide variety of settings and kind of modalities, so on and so forth. So anyway, again, this is not talk about that. I'm just kind of briefly flashing the results, but bottom line was that people did try very recently also to generalize power laws to something that could capture various nonlinearities. And yeah, we compared with those attempts, and it turned out that they couldn't capture things like inflection points or non-monotonicity, for example, double descent, multiple descent, and this functional form can. So bottom line, if you apply it to a bunch of different benchmarks, overall it was way better in terms of predicting performance than even those nonlinear kind of alternatives. And in terms of nonlinearities, again, not directly topic of this talk, but there are many examples where not the test loss or validation loss, but rather performance on particular downstream task does not at all behave as a straight line on log-log plot. That was original GPT-3 paper on arithmetic task, some clear kind of sharp transition. There were many others in that paper from last year. Basically, I'm just showing that depending on the metric you use, and yes, you can argue whether it's property of the problem or property of the metric. There is a recent paper on that. But depending on both problem you're solving and metric you use, the scaling can be anything, well, very far from linear. So you do need more generic scaling laws than the original naive power law. Anyway, so there was basically grokking example, and examples keep going on. So that broken neural scaling laws, the plus was that in principle, it can capture inflection points and nonlinearities, but in practice, of course, it's not silver bullet, and you do need to develop kind of good statistical approaches, and they are limited. Like if you have like very sharp nonlinearity and only few points very early, you might not be able to predict it. If you have a lot of points and you're sufficiently close to that break, and break is not too steep, you might be able to predict it. So anyway, I don't want to dive into that, but the promising things for this type of nonlinear scalings were that in the appendix of that paper, you can find many examples of recent papers and data taken from those papers were fit and predicted. It extrapolates, so it's not just fit. So they were extrapolated using this functional form, and it did quite well. And the list of things that it could handle was quite broad in terms of settings and various tasks and architectures and so on. But anyway, so that was kind of a useful thing that can be also used for the nonlinear behaviors of continual learning scaling, as we just saw. Switching to another example, how scale can help continual learning. I mean, last year there was also work by Alexei presented at this conference and a larger group of people. And that was another attempt to see in a bit different setting how scaling can help continual learning. Although unlike the previous paper, where the previous paper allowed fine-tuning of the model while doing continual learning subsequently, here, it was a bit different take. It was basically a hypothesis that maybe when you learn large-scale foundation models, they essentially end up learning good generic representations, and that's why maybe they generalize well. So example was CLIP, and instead of maybe doing continual learning in the raw data, that paper was essentially trying to do it on top of the representations learned by that CLIP model. Hoping that perhaps, yeah, I mean, if it's more generic, it will be easier to switch from task to task because, yeah, you don't look at the raw images, you look at the supposedly good representation of them. And indeed, that was a setting where you first kind of take whatever data from whatever tasks and continue learning, you just map it into the representation using frozen foundation model, like CLIP at that point, and then you do continual learning on top of that. Well, bottom line was, how I'm doing on time. Yeah, okay, so bottom line was that, yeah, so it did help. So when you had the, yeah, you were getting better accuracy on this kind of out of distribution streams, even though they were using like less pretraining data. And essentially, you also, yeah, you basically would do replay, which would be cheaper. Yeah, you need less data for that. And overall, the kind of pre-training on broader set of data would improve performance of continual learning and like downstream continual learning. So there are different ways in which large-scale models could be used later on for continual learning, and like overall conclusion is that typically they do help. But there are open questions that still need to be considered. For example, it could be that say they improve in terms of not forgetting, but can they possibly ossify and not be able eventually to adapt to very drastically different data? And when might it happen? And kind of how does it depend on the data differences between pre-training and continual learning, and within continual learning, and how do you measure those differences? So that's all kind of a good set of questions. Okay, so this is great, but as Saras was saying, like, what if we do want to train those foundation models ourselves? So later on, we could, I mean, we have more control on what we're training, how we're training, and also when we have potential access to compute and can train foundation models ourselves, the question could be, should we train them potentially in continual way as well? So that what I will talk about, it's like most recent also work in progress. But yeah, that will be next topic. But before we go there, I mean, there is a practical problem, right? So the problem is that you need compute, and typically in academia, at least so far, we didn't normally had it. And a couple of years ago, this basically the story of the collaboration that led to the recent efforts on building those open source models. A couple of years ago, because of this issue of lack of compute in academia, we and a bunch of other kind of groups were getting together. It's mainly open source groups such as like Lion, for example, in Europe, and Eluter, which was completely like not even like an official entity. Now they are non-profit. So basically a bunch of people were getting together on Discords and having discussions like how to get compute and so on. So the idea was that perhaps following the footsteps of like other sciences, like physics and Large Hadron Collider, for example, collaboration, we could also try to apply for the government-funded supercomputers. Because in a sense, I mean, there is this humongous, well, maybe not as large as a compute that actually companies have, especially like OpenAI, but quite large as compared to what we have. So for example, Summit supercomputer in Oak Ridge National Lab, which has roughly 27,000 GPUs. Well, there will be hundreds. It's kind of old machine relatively, but nevertheless, it will be replaced next year by Frontier, which is 40,000 GPUs. Okay, it's not exactly NVIDIA, it's AMD, but I mean, they're getting better in terms of their software stack. And for example, just we tried already, say, language model code such as GPT-NeoX. It does run on Frontier. So, I mean, it's possible to use those. Of course, those supercomputers were built with sciences like physics or chemistry and so on in mind, which usually means they are very good at data parallelism, but not necessarily kind of designed for a humongous model parallelism. Because physicists usually just like really have like humongous streams of data from super colliders, but they don't necessarily distribute their models as much as people do in AI, which is fine. I mean, you might not be able to build, I don't know, 200 billion parameter model on Frontier, or especially on Summit, but something 20 billion is fine. And on frontier, you probably can do 60, 70, maybe even up to 100. Oh, I don't know, we'll need to see. The point is also, there is a recent trend that maybe you don't necessarily have to build models that are that big in order for them to be quite useful. So the story is that we kind of joined forces with a bunch of people in academia, non-profit organizations, like I mentioned, Lion, which is kind of connected to Jülich Center, which also has their supercomputer. And some of the projects we actually were running on that Jewels. It's not as large as Summit, but it has 800s, which is nice. So yeah, I know, like it's sometimes a pain, but still it's compute that's out there, technically publicly available. You have to write applications from large collaborations. It takes time and reviewing, but at least it's a possibility. So anyway, there was this like huge collaboration that grows now. It's not started with Lion and Luther, and even like well, IBM joined, and Stanford and the Center for Foundation Models is most recent addition, together with a company together, and that was quite successful lately. I'll briefly mention that we managed to build state of art. Well, it doesn't stay state of art for long, but at that point it was relatively a kind of small model, like 7 billion, but it was like analog of Llama. I'll talk about that more. Anyway, so the collaboration grows, and the number of projects grows, and there are not necessarily language models that we're working on, but also multimodal. And it's not just kind of trying to improve capabilities. We're trying to keep an eye on how to make those models well, aligned, as it's called these days, in a sense that their output will not be like too offensive or just inappropriate, or like basically it will be what we would like to see and how to get there, just like pretty much everyone else who is working with language models. But with multimodal models, it's even trickier, because sometimes what the model says is okay, but it's not okay in the context of the image that it was shown to. Anyway, among those projects, as you can see, there is a continual learning that basically I'll talk a bit about that. That's the most recent work about continual pretraining. But yeah, before I jump there, indeed, as I said, this collaboration, especially with Stanford Center for Foundation Models recently, and the company together, and well, some people there were from ETH Zurich. Basically, that collaboration and our kind of inside project on Summit led to release of this model that tried to do completely open version of, for example, Llama. Before Llama 2 was out, it was May. Training started like end of April, and it took less than 4 weeks. The models were like size so 3B, 7B, and for a few weeks, I think they were kind of state of art, and they were on top of the Hugging Face kind of leaderboard in terms of evaluations such as Helm. But of course, I mean, right now there is like explosion. There is a whole zoo of these models. There are falcons, llamas, and whatever, you name it. But that was kind of example that, yes, you can build medium-sized models, and they can be pretty good, even though they might not be the absolute state of art like ChatGPT. For many practical purposes, they're good enough. And the idea with these collaborations is in longer term, just to keep getting more compute, whether it's supercomputers in different countries, and there are many, or kind of other ways. There are more and more clusters appearing, and trying to keep the open source community kind of efforts going. And I know it's a controversial topic, and I'm not going to dive into it right now, because there are pros and cons for open source. We can discuss it offline, but we're still leaning towards the fact that open source, even for safety reasons, is probably a better way to test the model, because it's transparent, and pretty much it's probably more powerful when the whole community is working with that model, developing and having some say in that, than if even like a grade testing team doing it behind closed doors. Anyway, as I said, topic is controversial, but it started as open source and there is lots of enthusiasm in the community. And in this way, I think it really accelerated progress in that open source large model field. But next question is, okay, so what continual learning or pre-training has to do with that? So how do people mainly train large models? Now, as we all know, it's practically always a fixed data set, which combines potentially multiple different diverse subsets of data. They could be as diverse as, for example, well, Gato is probably extreme example of that. There are just different modalities and totally different tasks. Yeah, essentially, sequences of decisions for playing games, text, images, and so on. But everything is mixed together, or well, you can say basically sample from each data set into each, like this picture from the Gato paper shows that you sample from all the data sets into every mini batch simultaneously. So of course, it's much kind of more bulletproof way of building a more general model than trying to do it sequentially. Like we all know, continual learning is hard. But yeah, I mean, same thing, of course, with language. It's like example of pile. You have like kitchen sink of all kind of different text data sets. And again, you mix them together and there is no issue that continual learning usually has because everything seems to be like multitask learning. But the problem is that the amount of data that are needed to build large models actually is increasing because since GPT-3 and the original power laws that I was showing by Jared Kaplan and those scaling laws, things were developing and the most kind of, I think, noticeable developments were the chinchilla model and llama models, like recent meta models, because essentially what they imply is that you should build smaller models with more data. And this was kind of a plot from one of the online blogs showing the trade-off between the number of parameters in the model and the X and the amount of data, and that chinchilla was quite small, say, comparing to Palm, but essentially it performed almost as good as that like humongous, almost like 500 billion model because it was trained on much more data. And overall bottom line between the original scaling laws paper and the chinchilla paper, the main change in the suggestion was if you want compute optimal training, which means, say, I increase the amount of compute by X, how should you invest that compute in terms of increase of the data versus increase of the model? The old scaling laws were suggesting 2 to 5, little bit to the data, more to the model. And it turned out, and chinchilla paper last year showed that that's not compute optimal. And actually, you should do closer to 50-50, which means the advent of smaller models that, if trained on humongous amount of data, will kind of be competitive with much larger ones. And that's what chinchilla indeed was at that point. And then, anyway, so like if you look at the chinchilla scaling laws, which basically combined like dependence on both the number of parameters and the amount of data, and is reducible entropy. So say you have infinite model, infinite data, you're still going to have some loss, and that's that E thing. But if you look at the decomposition of those parts of the loss in, say, large model that chinchilla was compared to, like Gopher, 280 parameters trained only on 300 billion tokens, you see that the model kind of contribution to loss it's kind of already small. So I mean, it kind of could have been much larger. It wouldn't really improve that part. So chinchilla instead, like using this different investment kind of strategy and training on 1.4 trillion tokens and smaller model, had actually overall smaller loss Yeah, so that was kind of the main change. And then this year we had llamas from Meta, and llamas went beyond chinchilla in terms of models get even smaller and the data get even larger. And one of the rationales was that when you talk about compute optimal scaling laws, you should probably also take into account not just the compute at the training time, but compute at the inference time. And for inference, the smaller the model is, the better. So if you have extra compute to burn, then maybe you should train on even much larger data than what Chinchilla would suggest for your model size. And Chinchilla paper has like a table with suggested model sizes and data sizes. So anyway, that's kind of what initial Llama kind of did. They had like 4 models from like very small, almost 7 billion, yeah, to 65, and they use pretty much this trillion tokens, which, as I recall, 1.4 trillion tokens would be chinchilla optimal for the 65 billion model, but they trained much smaller models on the same data. And yeah, the results were very good. The only problem at that point was Llama was not completely open. It didn't have like commercial license. So that's why our effort on that red pajama, reproducing the data set similar to what Llama paper did, and reproducing model at similar size like 7B. But the interesting observation from the recent Llama 2 paper, which, well, now is supposedly like completely open, including commercial license. If you try, and you see like how the performance kind of behaves with increasing amount of data, there is no sign of saturation yet, which makes you think that you probably should keep throwing more and more and more data on models of kind of modest size, because, well, we didn't get to saturation point yet. It might not be as compute like efficient, but there is room for improvement. But then here is an issue, right? So if you will need such humongous amounts of data to get to better and better performance, the data sets appearing kind of all the time. Like people put together, for example, like the red pajama, and then it's being cleaned and improved, and there is slim pajama. And then, well, before that, there was pile. Those data sets, like people keep creating them. I mean, there is a common crawl from which people like draw their data and clean it. There are other sources, there is code, and so on and so forth. Bottom line is that creation of data sets is very continual process naturally. And what was happening so far, every time there is a new kind of new and shiny data set, everybody jumps to train on that from scratch. So what about all the compute and all this effort that went into training all these previous models, like PTS suite, for example, from Eluter, that was, well, at that point, it was quite a good set of models of different size, from tiny, like 410 million, to actually 12 billion, was trained on Pile. Actually, nice framework for scaling laws, because you have the whole collection of those models. And now we have red pajama, slim pajama data set. So what do? Just like throw it away and train from scratch. So that was kind of our motivation, that, look, I mean, ideally we would like to somehow reuse that effort and compute, and actually people's effort that went into creation of such models, right? So can we do some kind of continual pre-training here, right? Yeah, but of course, there are reasons why people train from scratch, of course. As I said, just like with those classical examples, if you do have access to all the data so far, and you got new data, and you mix everything and train model in the multitask setting, you most likely gonna get better model than if you do it continually. I mean, that's an issue with continual learning. So the question is like, but we don't know how it all changes at scale. And say if you have sufficiently large pre-trained model, and then you start pre-training continually, why it's called continual pre-training rather than just continual learning, is that we're not really doing any supervised task. We just really keep, it's like continual unsupervised learning, just with a sequence of data. So perhaps there are some regimes where maybe you can do it and you can show that what you will learn is not that terribly worse than ideal case if you could mix all your data together. And perhaps you can do something about figuring out a method for doing that efficiently, whether it's learning rate schedule, or maybe you will need some replay. An open question is, would you even need any sophisticated continual learning algorithms if the original data set on which models pre-trained is large enough, model is large enough, and then you just keep adding new data in the future? Everything may change with scale. So I think that is still kind of open question, which is under researched. And we kind of started looking into that in the context of this project on Summit. There's basically a bunch of students here, some of them in the in the audience, like Adam. Sorry, misspelled your name. I mean, yeah, Adam Ibrahim, and she teaches. Anyway, so it's basically all the people on the Insight project on Summit. We just kind of wanted to explore what happens if we take this PTA suite of models from Eluter, and we, instead of training from scratch, try to train it on Red Pajama or Slim Pajama, so on and so forth. And the very first question we ran into, like mundane question of like learning rate schedule, right? When you switch from one data set to another one, what should you do? Like, should you rewarm your model, and how you should do that? And we kind of, let me see, I have 7 minutes left. I'll go quickly, but there is a paper online. It was presented in that efficient systems for foundation models workshop, which is actually was organized by Together and Stanford Center for Foundation Models. So it was at ACML, paper is out there, and you can look at that. But bottom line was, yeah, so you would think intuitively that if you increase learning rate, it should help to adapt better. But if it's too high, then you might just forget everything that you learned before, and essentially like learning from scratch on the new data, so you can defeats your purpose. So the experiments on Summit, upstream means the old data set pile, because that's what PTA was trained on. We just used it, was 300 billion tokens. Downstream data was Slim Pajama, which is essentially, I know, I mean, there is proliferation of this data set. Together released Red Pajama, and then Cerebras, which is a hardware company, but they're also kind of doing a lot of language modeling. They're also in the Bay Area. They just cleaned the data set, deduplicated it really well. And anyway, so it was like half the size of the original one. But we made sure that we kind of just use comparable amount of data between the old and new data set for this continual pre-training kind of setting. And linear warm-up, cosine decay schedule, kind of standard things. It was a language model that pretty much a workhorse behind all the open source projects. This GPT-NeoX is the code base that was used for PTA, was used for stability language models, and we used it also for the Red Pajama Insight. And anyway, so there are mainly like two code bases, the GPT-NeoX and the one like the Megatron Deep Speed that Bloom was trained on, and some others. Anyway, we took relatively small model, like 400 million, to run experiments quickly, and basically made a few observations. So like how long you should warm up, like for how much kind of data of the new data set you should do that. So basically, it doesn't seem to be like that terribly important, at least in this specific experiment. So as I said, it's work in progress because it might be data specific, a particular like combination of data sets and so on and so forth. So that's why we need to keep exploring those questions across wider range of different data sets and kind of settings. So what was kind of probably more important, oops, just a second. happened with 2? Sorry, I don't know what happened with it, but I think it's kind of switched. Okay, well, it's in the conclusion. Anyway, so we also try to, basically, we looked at the most important thing was, and now I cannot find the slide, like how high should be the max learning rate. And then what happens if you just start rewarming on the same data? So essentially, would you like see the sharp increase in loss when you're doing warm up? Is it like due to distribution shift, right? So, and also like how the maximum learning rate affects that. Like, is it the jump higher when the learning rate is higher? Yeah, so if you do it, what will happen if you do it on the same data so there is no distribution shift? Yeah, we explored that, and yeah, I think I'm running out of time already. And what happens if you also train from some previous checkpoints of that model, even though they didn't yet converge? And bottom line, I mean, that didn't really matter. So basically, kind of conclusion, well, basically we're trying to see if there are any drastic kind of things that the aspects of learning rate schedule may impose on this, and at least to make sure that there is nothing that we overlooked. And like bottom line was, okay, so just like takeaway lessons. Yeah, so warming up kind of helps. And we were like training on slim pajama after pile. Continually pre-trained models did better than models trained from scratch. And essentially, we should keep doing that. There are many more data sets. It's just like one switch from one to another. And definitely we need to, it's just like more or less anecdotal kind of evaluation. It depends on the data sets and depends on the probably model sizes. So we need to make sure that even just with learning rate, we will not see any surprises. Another question would be like, what else can help? We should try like replay and other methods, but probably we should start with something simple. And okay, I'll just skip that. But basically what I just wanted to say before I conclude, step back to the scaling laws. Perhaps what would be also interesting to explore here is kind of a trade-off between parameters that you control in those models, like size, model size, architecture, other properties, and data, also size and perhaps diversity, versus things that you do not control. For example, you pre-train your model, now you're doing continual learning on top of that, and you have no idea how complex the downstream task is, right? So perhaps something like perhaps relative or whatever you name them, scaling laws would be helpful in practice. Say, if I'm a company building foundation models, and I know that somebody gonna be using them in their kind of continual learning settings, how much I should invest into like building that model? Should it be like, how large should it be and how much data it should be pre-trained on, and questions like that. It probably really depends on the application. So if people are going to be doing some relatively simple experiments, I mean, it's of course like just exaggeration, but if somebody going to be just using my model to do 10 rotated MNIST tasks, I probably should just ship them much smaller model than if somebody gonna, I don't know, play thousands of video games or try to send robot to Mars. So something tells me that more pre-training and larger model may be required to kind of compensate for that complexity. But we do need to formalize what does it mean for the subsequent continual learning task to be less complex, more complex, and what are the variables that go into that complexity, which clearly relates not just to number of subsequent tasks, but to their diversity and some other notions of complexity. So that's why this is like a hand-wavy slide, but that's where I think things are also under-researched. Anyway, I think I'm out of time. So are there any questions?
how does this scaling loss look like for reinforcement learning?
Okay, so yeah, there are also scaling laws for reinforcement learning. I think, I mean, might not have it right here, or I may, but in that broken neural scaling laws, we also have examples of kind of fitting that to what people were reporting in other papers as a results. And I mean, bottom line, yeah, there are scaling laws papers for reinforcement learning, and depends on the setting. But yes, so there are several studies on that. And why I also mentioned the broken neural scaling laws, because they're not always actually quite linear. That's why we also looked into those. But yeah, so I think there are quite a few papers by this day. Yeah, I cannot find, I think there was a plot somewhere. What? Yeah, so I think it was, yeah. So there, anyway, yeah. So basically, the papers in the appendix of broken neural scaling laws paper, where this picture kind of was produced, those references would be at least a starting point. But I think there is much more right now. It was just like just to show that those scaling plots can be also captured by this functional form. It's just like to give you some reference where to look. And I'm pretty sure the scaling laws papers proliferate quite quickly everywhere, including reinforcement learning domain.
Thanks a lot for the talk. Personally, I have an issue with the word law, scaling laws.
Yeah.
My question is, to what extent do you think we should invest more in understanding the assumptions made by scaling? Because it's such a rigid scheme in which you have to run those things to get those curves. Are we like missing out a lot because all the assumptions of how we're supposed to train the model?
So basically, I mean, it is okay. I agree that the word law can be triggering because indeed it's almost it's making the analogy with, okay, I mean, it's still hypothesis whether you can say that just like there are natural physics laws, there are indeed scaling laws of performance with those artificial models. And since physicists got to it first, right, like Jared and others, they kind of looked for laws in artificial systems just like they would do it in the natural system. So I think it's, okay, of course, at lower scales, clearly many other things matter. That's why I kind of was putting more stuff here with those dots, that it might be architecture and all kind of other aspects.
Sorry, but you think
Yeah.
at large scale that those don't matter? Like in my mind they matter, it's just we don't know because we haven't checked.
I don't know. Yeah, it might be that they are not the right laws. Just like everybody thought that Jared's compute optimal was compute optimal. And if you do more experiments, then you see that it wasn't compute optimal. So those laws may be like refuted and replaced by better laws. But I think it's likely, just like with the law of large numbers, that even though at smaller scale things look kind of messy, at sufficiently large scale there should be some regularities. We just might not be necessarily having complete knowledge of all the variables that we should look into, or functional forms. That's why we started, okay, it's far from straight. So, but I think there are laws. It's just like our path to them may go through some incorrect laws.
Thank you.
Data is much more important than model size from where I got. Why are we missing as academics to get something like ChatGPT 3? Is it just multiple aspects?
When I said model can be smaller, it's still quite large.
Yeah, no, but you already have access to that one, right? You already have access to the data.
Okay, so basically, but even if you have access to 7 billion models and so on, yeah, so I mean, you can keep training, you still need some some amount of compute to keep training, say, 7 billion model on some huge amounts of further data. I mean, when I said it's small, it's not millions, it still may be, it has to get to a certain size to start performing decently. And yes, you could keep training, but it's still not, you probably cannot do it on 1-2 GPUs. Yeah, so that's kind of like anything like 20 billion models or whatever, like GPT-NeoX, definitely. Yeah, so you do need multiple GPUs, and especially if you're also gonna have a humongous amount of data, which all this suggests. Yeah, so you need, well, okay, that's a good question, like how much compute you need to do that and what the estimate would be, but something tells me it might be, well, it might be more than millocluster, and or they will not let me use it just for my project for the next 6 months. So yeah, so the compute is still needed. Yes. So yeah, that's a good question about new optimizers indeed, because indeed a few months ago there was some new optimizer proposed which was making things considerably more efficient. I think Sophia, right? Yeah. So yeah, there could be still breakthroughs which make learning much more efficient. So another kind of interesting thing with optimizers potentially is with very large amounts of data. For example, when GPT-3 was trained, as I understand, there were no multiple epochs. So normally with extremely large amounts of data, people don't do multiple epochs, so it's online training. When you do online training, then the notion of overfitting is kind of disappearing. So the whole reason the complex optimization algorithms were kind of thrown away because they would overfit, right, on relatively small data. They could find better solution of the optimizer, but it will not generalize well. And then with online learning, things change. So potentially, I mean, essentially like your training error and your test error kind of close. So maybe there is a hope for better optimizers that would overfit before to be applied to online setting, and they will be actually doing well. I don't know. It's just a thought. Sorry, I didn't hear.
I was just wondering if you've tried or sort of testing like a simple optimizer, just the learning rate without really complex scheduler.
Oh, you mean just like not using Adam?
Yeah.
Yeah.
Would that help?
Yeah, I mean, yeah, we need to ask Adam here. Yeah. I maybe in the beginning we did, but I think, yeah. Yeah. So in this specific experiments, I'm pretty sure we did try in the beginning. Yeah.
We are running out of time.
Okay.
Okay, let's thank Irina once again.
That's yours.